grab your seat, okay? Okay, interval notation. You guys are actually really going to like this notation. We can use interval notation for a couple of different things. One of the things that we use it for is stating domain and range, and it just makes our life like way easier than when we did domain and range in grade 11. So grade 11, we learned how to do sort of like these long sentences. It was like, X is an element of the set of real numbers, such that, and then we had to do all that stuff with the inequalities and all that good stuff. This is another way that we can do that, but it simplifies it a little bit. It's a really nice notation. And other things that we can use this notation for would be like if we're expressing something on a number line, expressing any type of inequality. We can use it if we want to state where a graph is increasing or decreasing, or where a graph is positive. All of those things. We can use this for lots of different things. Okay, so here is the idea. If I want to say that something goes from a lower number to a higher number, I will start with the lower number, and then I will put a comma in between, and I will end with the higher number. It looks like a coordinate, like an xy coordinate, but this is just simply an interval notation saying, oh, it goes, the number line or the domain or whatever it is, goes from -3 to 5. Now, if we look at this example here and what we see on the number line, one of these has a round bracket and one of these has a square bracket. Why would one have a round bracket and why would one have the square bracket? What's the difference here? Surwa?
Square bracket is when the end behavior is shown, like on the graph.
So what do you mean? Let's not use the word end behavior because that would require a polynomial, right? So what do you notice on this line that is different from between -3 and 5? I think that's what you're trying to say, but.
Like,
no. No? Okay. Somebody jump in here. Sam, what do you notice? Okay, so 5 is a solid point. -3, we learned about these like hollow points last year where everything up to but not that number is included in the set. So everything up to but not including -3. So like -2.9999999999999 is included, except then when we hop to -3, that's not included in the set.
Why is it like that?
Because it has a hollow point. So it's just saying everything up to but not including -3. If it has a solid point, then it's everything up to and also including 5.
Is there like a
Okay?
reason for that, or is it just math?
This is just like the visual of, we'll sort of put together some things. But yeah, this is just like a number line visual of that. But we may see some things where this is relevant. So you know how in inequalities we have greater than or equal to? That's, I guess maybe this answers your question a little bit, Andreas, but if we have just a greater than or a less than, that would be like a round bracket because we include all the way up to but not including that number. If we have a less than or equal to or greater than or equal to, we use square bracket to include that number in the set. Okay, so let's look at this chart here. So you will notice everything that has a hollow point here. If we compare this to what the interval notation looks like for this, this is A to B, but we don't want to include A and B in the set, so we use round brackets on both of those if we look at this example here. This one is A to B, but A is a hollow point, B is a solid point. So B is included, A is not included, so notice the round bracket on A, the square bracket on B. Vice versa for this one, right? B now has the hollow point on it, so B is not included, so we use square for A, round for B. 2 solid points, we include both of them in the set. All the way from A up to and including B. 2 square brackets. Okay, notice this one. We start with a solid point and it goes on to infinity forever. So A is a solid point, it's included in the set, square bracket. And then we have the infinity notation here. Why would I not put a square bracket on infinity? Rebecca, what do you think?
Because the square bracket kind of means that number, that n number is in it, but like infinity
can't put a cap on infinity, right? Infinity goes forever. So Rebecca's right. When we put a square bracket, we're saying, oh, it ends here, and we're including it in the set. But how do we do that with infinity? Because infinity never ends, right? Let's look at the reverse. We have a solid point here, but we're going forever toward the left. So this one goes from negative infinity, the lower bound, all the way up to and including a square bracket, because it's a solid point. Okay, and then we can see some of these other things too. Hollow points, same example, but with hollow points, we just have a round bracket on A instead. And then this one, forever toward the left, forever toward the right, the way that we say that is negative infinity all the way to positive infinity. Round brackets on those because we can't include them. Okay, so that's a lot of info, right? Let's summarize this and just write ourselves a quick note for interval notation here. Okay, if you don't have room on your worksheet to do this, find an extra paper that you can add this to. So interval notation. Okay, so a couple uses that we talked about are in place of domain and range. The longer sentences that we made in grade 11 could be used in place of an inequality. So anything with greater thans, less thans, greater than, less than, or equal to, those types of symbols. We could use it for increasing and decreasing areas of the graph to express that. Or we could use it for positive and negative sections of the graph. Okay, so lots of different things that we can use this for. We will have, always, when we do interval notation, lower bound to upper bound. Okay, and it looks almost like a coordinate. So it's the lower bound, comma, the upper bound. And we will have square brackets or round brackets depending on what we have. Is it included in the set? Is it not included in the set? Is it an infinity? And so on. So square bracket means the value is included in the set. Okay, so up to and including that number. Okay, solid point or equal to that number. Round bracket means the value is not included in the set. So all the way up to, but not including that number. Okay, negative and positive infinity always have a round bracket because they can't be contained, right? They will go on forever, as Rebecca said. Okay, so for right now, I'm going to do one homework question from number 1, and we'll do the first one from number 3, and then you guys will do the other ones. So I want to do one I, domain and range. just so that we can remind ourselves of domain and range. And again, as Surwa had mentioned before, the graphing software doesn't really put those arrows on for us, but we have to kind of sort of assume that there's arrows on these ends here. Okay, somebody tell me, what is domain? What are we looking for when I say I want you to tell me domain? Thinking back to grade 11 now. Kenzie? Any value that x can take. I like to think of this as like the left boundary and the right boundary, if there are any. Okay? So for domain, we'll still use that like capital D to indicate that we're doing domain. And all I really like to think about here is my graph ever going to stop going toward the left? Is my graph ever going to stop going toward the right, if I think about my graph this way? And are there any gaps in between or anything that I need to consider? So do we have a left boundary or a right boundary here at all? So instead of, usually in grade 11, you guys don't have to write this, we would say this, x is an element of all real numbers, and we wouldn't put any restrictions on that. Now, because it's literally everything, I want to say everything from negative infinity to positive infinity. So I'm going to say it like this, round bracket, negative infinity, lower boundary, upper boundary, infinity. Always with round brackets on any negative infinity or positive infinity. I'm just saying it's everything. X can be anything, right? Okay, explain to me what is range. What am I asking for when I ask for that? Rebecca. Okay, any value that y can be going up and down. Again, we always start lower boundary to upper boundary, so bottom to top here. So any thoughts on what domain might be here? And you can give me the boundaries, but if you can give it to me in interval notation, then brownie points on top of that. Michael? Okay. So sorry, square bracket? Good. Very nice. 1 is the lower boundary here, and then my graph goes up forever to infinity. Okay, 1 is also included in this set with the square bracket because 1 is actually a point on the graph. Okay? Make sense? Okay, so domain left to right, lower bound to upper bound, range bottom to top. Andreas?
How do you know domain is like infinity? Wouldn't it be like negative one or something?
So you have to imagine, like think about these arrows here. You have to imagine this is going to keep going, right? It's just going to keep getting wider and wider and wider forever as it continues. So it will keep going forever toward the left and forever toward the right. Okay? So you just have to imagine what that graph is going to continue doing as it goes off here. Okay, let's see if we can do 3A for this. And then the other 1 IIIs and the 3B will be your task to come back to. How do I state interval notation if I want to state this on the number line? Matt, what would you do?
Put 4 in a soft or a round bracket,
Okay,
and then infinity, and with ending in a round bracket.
and comma in between, right? Perfect. 4 is a hollow point. It's not a solid point, so we're including everything up to, or everything after, but not including 4. So like 4.000000001, but not 4. Okay? Much easier than inequalities, in my opinion. So this is a really nice method here. Okay, so we will come back to that. Everyone got that? We're good? Any questions? Okay. We will come back to, like when you guys have time to work, make sure you go back to 1 III and the last one for 3. You might even be able to jot down the last one for 3 quickly right now. And we're going to move to Unit 1, Lesson 3 here. We'll see what we get to today. I will make sure that you guys have some time before we leave to do some work. Okay, turning points and zeros. So in our first section for today, we learned how to predict end behavior. We're going to take a look at different turning points and zeros that we can have for a variety of degrees and see if we can pull out some patterns like we did in our first lesson. So I just wanted to make a note as well. Somebody from my other class asked me, what if you have a straight line, like a horizontal line? And that actually would not be included in our polynomial type functions because a horizontal line is really just y equals a constant. So we actually don't really include that in our polynomials. We start at degree 1. Constant is almost like it's degree 0, right? So we always start sort of at degree 1 and move forward from there. Okay, degree 1. This is anything that is a line with some sort of slope that is not undefined. So a vertical line or a constant, like horizontal line. So any line that you can draw like this, whatever, has to have some sort of slope. That's really the only option, right? Either it has a positive slope or it has a negative slope. There's not too many other things that can happen with a line. So as we start to go here, we're going to include possible number of turning points and possible number of zeros as we do our sketches here. So if I have a line, what are the possible number of turning points? What is always going to happen if I draw a line here? 0. Okay, so lines do not have turning points because they don't have curves. They don't go from increasing to decreasing or vice versa. Possible number of zeros. If I must have some sort of slope on here, what has to happen here? Kenzie? It has to be 1, 0. And again, we do not include that horizontal line as part of that because that's a constant. That's like degree 0. So degree 1 always has to have some sort of slope to it. Okay, so the only possibility here is that there has to be 1, 0. That's it for degree 1. Okay, let's look at a couple options for degree 2. So degree 2, this is like our quadratic that we talked about. We could have maybe like our usual, like something like this would probably be a common option. We could have something like this where the vertex like sits on the axis. Maybe it opens down, maybe it opens up. Or we could also have, what would be the last option here as far as like how this could cross the x-axis? Any ideas here? Keaton? Not for a quadratic. That's a different functional. It's not even a function, actually. Ian, what do you think?
It could just like not cross the x-axis.
And how would that happen?
Like if you put it above y0 and then opening upwards.
Yep. Like this or like this, right? Opening up above the x-axis, opening down below the x-axis. Okay. So here's our options for turning points and zeros. What is always going to happen with a simple degree 2 parabola as far as turning points? Serena?
There's gonna be 1.
There must be 1. Could there be 0? Could there be more than 1? No, it's just very simple U shape. It's only going to turn once. Okay, how about possible number of zeros here? What do we see as far as number of x-intercept options? Michael? So there can be 2. What other possibilities do we have, Kenzie? 0, 1, or 2. Perfect. Depends where that quadratic is, right? How it's shifted and how it's opening. Okay, we're going to start to see some patterns emerge as we see some more pictures here. Okay, degree 3. Yep, Keaton? Sure. So the 1 happens if your vertex is sort of just like sitting on your x-axis, like so. Yeah. Okay, degree 3. So degree 3 can have a couple things that happen. Degree 3, depending on the other things that are in that polynomial equation, could be like a really simple sort of like curve, like so. Could go upwards, could go downwards, like this. In this scenario, how many turning points do we have? How many zeros do we have? What are the options here? Zach? Okay. No turning points, 1, 0. That's the first scenario. Now, if I were to start adding some other terms in here, maybe I add like in addition to an x cubed, maybe there's like an x squared and an x. Sometimes what happens is the s becomes more pronounced and it sort of like curves a bit more. So what can happen is we saw one of these in our homework, we'll get something like this. Okay, the s is more pronounced, and I'm seeing that we're crossing the x-axis twice here rather than once now. Okay, this little mountain is just grazing the x-axis there. So could have two x-intercepts. Oh, sorry, that's turning points. Could have two x-intercepts. And how many turning points would be in this one? Also 2. So there's one here and there's one down here. So could have 0 or 2 turning points. And then if you imagine that I just take this graph and I knock it up just like a little bit, shift it up, then we are now seeing 1, 2, 3 x-intercepts, but same number of turning points, right? We just have 2. So we'll add possible number of zeros here. Could be 1, 2, or 3. Possible number of turning points here, depending on how pronounced that s is, it could be 0 or it could be 2. Okay, once we do degree 4, you will start to see the patterns. So degree 4, I've got a lot of I've got a lot of pictures here, a lot of options. Okay, degree 4, we know this looks similar to a quadratic. So we could have a simple degree 4, right? We could have something maybe like, maybe we could have a degree 4 has like a bit of a square base. Maybe it doesn't have any zeros, right? Maybe it just like opens above the x-axis, like so. So what are the turning point options and the x-intercept options for this scenario here? Sarwa?
1 turning point and then 0, zeros.
Okay, so that's the first option. If I were to add in some more terms in here, it's not just an x to the 4, but now maybe in my equation I have like an x cubed, I have an x squared, I have an x. What starts to happen is this still will have a basic U shape, but sometimes we get little squigglies in between, stuff like that. So what could happen is I could have maybe something that does this once I start adding more terms in here. Okay, and this one is just grazing the x-axis here. Turning points, what are the turning point options for this one? What are the possible number of zeros for this scenario? Keaton? Okay, so 3 turning points, 1, 0. Now I'm just going to start to slide this guy down a little bit as we go. So I could have, if I slide this down, or if I have a similar shape to this and it goes like this, I still have 3 turning points, but I now have 2 x-intercepts, so we're going to add that to the list. Okay, and you can probably imagine what happens like if I shift this down like so. I could have now 1, 2, 3, so we'll add that to our list. And then if I shifted it down like a tiny bit once more, I could have 1, 2, 3, and 4. That's the max that I'm going to get. I can go all the way from 0 all the way up to 4. And note that this is degree 4. Okay, without pictures, we're going to see if we can predict, based on what we found out about 1, 2, 3, and 4, we're going to see if we can predict what's going to happen with 5. And keep in mind, usually like odd degree polynomials will follow similar trends, and even degree polynomials will follow similar trends. So what are we noticing about number of turning points for the for the odd degrees? Because this is now an odd degree here. Question? Yep.
So they use like the degree 1, 2, 3, 4. Those are the power functions?
Yep.
Okay.
But they can also be polynomials. Like, so this is like a basic probably power function, but this is more like if I had something like x to the 4 plus maybe 3x cubed minus 7x squared. That's why we get these little curves that start to happen in between. Okay, I don't know that that equation is going to produce this. I'm just saying that's what happens. Okay. What are we noticing about turning points of odd degree polynomials here? Give me one observation that you're seeing. Nick? The turning points are even. Okay, I like that. What else? Erie?
They all have like 0.
Okay, they all start with 0, so the minimum would be 0. How high can they go? Look at this one. How high is it going in relation to the degree? Nick? So it's like 1 less than the degree. So any guesses on what the possibilities might be for turning points for 5? Keaton?
2 and 4.
Yes, 0, 2, or 4. So Nick said the turning points are even. He's correct. So if your degree is odd, in order for that to have opposite end behavior, it has to turn an even number of times. So if I start down and I turn twice, my ends are opposite. But if I'm going to turn 3 times and I start down, 1, 2, 3, I'm going to end down, right? So opposite number of, or opposite even odd turning points. Okay, let's look at zeros. Follow the trend of the odd, so 1 and 3. What do we notice about these ones? Matt?
Like the possible numbers of 0 is like degree.
Okay, can go up to the degree. What about the least number of zeros for both of these? What are we noticing? It has to be 1. So what would be my list for degree 5? 1, 2, 3, 4, 5. Perfect. Okay. We're going to consolidate this on the next page, and we'll talk about evens as well, because evens are a little bit different. You might start to see some patterns with the evens also. Okay, so number of turning points depends on the degree. If the degree is even, a polynomial of degree n, so that's just a placeholder, has some degree that's even, has a maximum of blank number of turning points. So if the degree is n, and I am looking at even, so we talked about odd, what's the max?
1 less.
1 less than n. So how do I say 1 less than n? N minus 1 turning points. So 1 less than the degree is what we're saying. Okay, and a minimum. What is the minimum number of turning points for an even or U-shaped polynomial? What do we see here under turning points? Sarwa?
0.
Evens.
1.
1. Okay, so both of these have. If I have something that's U-shaped, guys, that has to turn once, right? If it's U-shaped facing down or U-shaped facing up, it must turn at least once for the ends to start up and end up, right? It's got to turn in between there. So it has a minimum of 1 turning point. Okay, odd degree polynomial, it actually follows, the maximum follows a similar thing. We said the max of the odds will also go up to 1 less than the degree. So if it's 5, 3, or 1, notice that the turning points will only go up to 1 less than that degree, 4, 2, and 0. So that is also an n minus 1. So if the degree is n, my number of turning points are 1 less than that, n minus 1. Okay, so same thing as up here, 1 less than the degree. What is the minimum number of turning points for an odd or S-shaped polynomial? Michael? Must be 0. Okay, because I could have a slight S curve that would have no turning points, or I can have it more pronounced. Okay, so when a polynomial has a certain number, k turning points, the least possible degree, also known as the most likely degree, sometimes I like to say lowest possible degree. Sometimes that makes a little bit more difference. The lowest possible degree, also known as the most likely degree, is 1 more than the number of turning points. So if I look at this, for instance, these are good examples. If I count the number of turning points, 1, 2, 3, the most likely degree of this polynomial is degree 4. It's 1 more than the number of turning points. That's typically what happens. This does not follow that same thing. We're just saying it's the most likely, and it's also the lowest possible degree. So if I have 3 turning points, I cannot have anything lower than a degree 4 polynomial. Could also be degree 6 or degree 8, but it can't be any lower than one more than the number of turning points. So we're going to say most likely is k plus 1, turning points plus 1. Okay, so if I count up the number of turning points, if I have 5 turning points, that polynomial has to be degree 6 or higher. Okay, always one more than the number of turning points. And it's most likely degree 6. Number of zeros, let's consolidate what we figured out in our chart here. When the degree is even, a polynomial of degree n has a maximum of blank zeros. Look at your chart. What is the maximum number of zeros that an even polynomial can have in relation to its degree? Keaton? It goes up to and equal to the degree. So all the evens, a degree 4 can have up to 4 zeros. A degree 2 can have up to 2 zeros. Okay, that's the max. So it will be equal to the degree. You cannot have more zeros than your degree. So if I have a degree 5 polynomial, I won't ever have more than 5 zeros. I could have less, but I won't have more than 5. How about minimum number of zeros for an even degree polynomial? Sarah?
0.
It is 0. So if we look at our chart here, we can see all evens, so 2 and 4, could potentially have 0 zeros. They don't cross the x-axis at all because they're U-shaped, right? So if it's U-shaped and it's over the x-axis and facing up, I don't have any zeros, or vice versa, under facing down. Okay, odds, maximum number of zeros for any odd degree polynomial. What do you see in the chart for zeros? Kenzie? N, so equal to the degree, right? 1 can have up to 1, 3 can have up to 3, and 5 can have up to 5, and so on. So it will be n. What about minimum number of zeros for an odd degree polynomial? What are we seeing in the chart, Matt?
1.
Must have 1 0. Very nice. Okay. This is sort of just like recognizing patterns. Most of this unit is just recognizing patterns, predicting shapes and things like that. What different things can we have? Okay, so I want you guys to think about, you can chat with your partner about this, so people sitting next to you. Explain why an odd degree polynomial must have at least 1 0. I'm thinking here about end behavior. So what about the end behavior tells you that an odd degree polynomial has to have 1 0? And why does an even degree polynomial have to have at least 1 turning point? Think about the end behavior. So see if you and your partner can come up with some statements for these. All right.
It's 5 and it works.
Why does an odd degree polynomial have to have 1 0? What do we know about them that tells us this? Rebecca.
Because the ends are both like they're opposite, it doesn't make sense for it to have no zeros because it will have to cross the x-axis if it goes first.
Agreed?
I agree.
Odd degree polynomials always have opposite end behavior. And that means that because I have opposite end behavior, my graph either starts facing down and ends facing up, or vice versa. Somewhere in the middle, in order for that to happen, it's going to cross the x-axis. It has to have some sort of area in between here where it crosses the x-axis. So opposite end behavior tells us it must cross the x-axis on its way from a lower quadrant to an upper quadrant, or an upper quadrant to a lower quadrant. So either it's going from quadrant 3 to quadrant 1, or it's going from quadrant 2 to quadrant 4. And in order for that to happen, Okay, so this is the other option. In order for that to happen, the only way that that's going to happen is if the graph crosses once over the x-axis, or it could happen more, right, if the s is more pronounced, but it has to at least go once. Okay, what about the second one here? What happens if, or why does an even degree polynomial have to have a turning point? At least one. Nick? Yeah, so it's U-shaped. So in order for that to happen, of course, we must turn somewhere in between. Do you have something to add, Rebecca?
Is there like a possibility it could just be a straight line, so there is no turn here?
Not for even. So if it's a straight line, that means it's degree 1. So that would be odd.
Oh, yeah, okay.
Yeah. Yeah?
Yeah, and then behaviors directly both so it has to.
Okay, so it has to have the same end behavior. So if I start facing up and my end finishes facing up, it must have turned somewhere in there for that to happen, or vice versa. If I start facing down and I end facing down, something must have happened in there where my graph curved for that to happen. Okay, so because it has the same end behavior, and it's U-shaped, so they will either go from quadrant 2 to quadrant 1, or quadrant 3 to quadrant 4. So as a visual example here, they are both facing up, or the ends are both facing down in these bottom quadrants. So something happened in between here where I had to turn for that to happen, right? Same thing here. Something happened where I have to turn in order for that to happen. Usually we go left end to right end. So this is 3 and this is 4. Normally we'd say 3 to 4. Okay, these would be great communication questions on a test, don't you think? I think so. Sarah was like, nah, I don't think so. Okay, wink, wink, nudge, nudge. These would be great communication questions on a test. All right. We are almost to the end here, very, very close. Okay, so I think we should be able to do like degree, leading coefficient, basic shape, and behavior. So I'm going to give you guys a couple seconds, see if you can fill those out. And based on our summary that we did above, I want you to see if you can fill out the possible max and min number of zeros. I can do this simply by knowing the degree of the polynomial. So I don't need to know anything else to determine max and min. These are just possibilities, right? We don't know exactly what this graph looks like. I don't even know exactly what this graph looks like. Okay, so a couple seconds to see if you can fill that out.